video session, we are going to start a new topic on process and the memory. Let's discuss the various topics that we are going to study. We are going to study about the process and the program, the process ID, the parent process ID, the memory layout of the process, and example of different memory sections of the process using a C code. Before proceeding to the process and the program, let us see what is the steps involved in compilation of C source code. Here we have the program or the source code. We have several source code together written in the project, and the preprocessor preprocesses all different source codes, and then the compiler and assembler converts the preprocessed code into an object file. Then the linker takes the object file and the library together to form an executable file. There are different formats of executables supported in Linux system. Some are out format, POF format, and ELF format. Now these executables are loaded onto the memory using a loader. So a program written in the high-level language finds its way onto the memory. This is a program, and the instance of the program running in the memory is called process. So a process is an instance of executing program, whereas program is a human understandable file containing the information that describes how to construct a process at runtime. Now let us see an example between program and the process. In this small C program, we have written a very basic program to print the output onto the screen. This is called as a program. Now let's compile this program using the GCC compiler. And in this case, we are creating an output file called as process_demo. This process_demo is an executable file. Now let's execute the program. When we run the executable of a program, it is called as a process. So a process is the instance of executing program. This process is created in the memory, and once the process is terminated, the process no longer exists in the memory. In next video session, we will learn process ID and parent process ID. Thank you. Hello and welcome. In this video session, we will discuss process and its ID. Each process in Linux has a unique identifier called as PID or process ID. A process is created by its parent process. In Linux, we have a parent and child process relationship. In Linux, the first process that is being created is the swapper process, and it has the process ID 0. The swapper process in turn forks the new process called as the INIT process, and the INIT process has process ID equal to 1. INIT process plays an important role in Linux systems. It creates and monitors a set of other processes. INIT process also becomes the parent of any orphan process. We will discuss more on the orphan process and fork system call in upcoming video sessions. For more information on INIT process, we can see the manual pages. This manual page can be referred for more information on INIT process. Now let's see what is process ID. We can get the ID of a running process using system call getPID. This is the syntax of getPID. We need to include unistd.h in order to use getPID. GetPID system call does not take any argument, and it returns the ID of process from where it is called. In a 32-bit Linux system, we can have up to 32768 maximum process. We can get the information of maximum supported process in system by reading this file. In case of 64-bit Linux system, the value is much higher. Let's see an example for this. In our case, the Linux system is 64-bit. Let's read the file content here. So, from this, we can see that on a 64-bit Linux system supports 4194304 maximum number of process. As a note, the process ID starts from 0. We can get the list of all the process running in system by running ps-ef. Let's see this. ps-ef is the command. We have got the list of process and its details that is running at this moment. First column is the UID, that is user ID, who has created the process, followed by PID, which is nothing but the process ID. The third column is the PPID. This is nothing but parent process ID. Here, let's take PID 10, 11 and 12. These processes are created by its parent whose process ID is 2. This means the PPID of process 10, 11, 12 is 2. Similar to get PID, the system call to get the parent process ID is called get PPID. Let's say this with example program. Here we have a simple example which gives the ID of current running process using get PID. And we can also get the parent process ID by calling get PPID. As discussed in Linux, everything is considered as a process. So, when we run this program, a new process is created by its parent process. We will run this program and examine its output. Let's compile the code and generate the output file called process_demo. Now, let's execute this program. In other tab, let's run ps-ef command and check the PID and PPID. Here we can see process_demo's PID and its parent process ID, that is PPID. Let's examine the output of process_demo. We can see that we have got same PID and PPID as we saw by running ps-ef command. So here, when we run /process_demo from shell or terminal, this shell is the parent process and it pokes a child process and creates process_demo program. Let's run the program again. Now, if we observe the process ID is different from previous executed process ID, this means process ID is not fixed and it varies from execution to execution. But during execution, the process ID is unique, which means no other process can have same process ID. When the process terminates, this process ID is given back to system and Linux can reuse this process ID later. Also, if we observe, when we execute the program every time, the PID is changing, whereas the PPID is same because the shell that is executing the program is same. Now let's execute the same program from other terminal. We can see that the PPID is now changing. So with this we can also infer that each terminal is executing as a unique process ID. In next video session, we will learn more about process states. Thank you. Hello and welcome. In this video session, we will discuss on the process and the different states in which it can exist. A process is created using the fork system call, and we say that the process is in created state. The process can be in running state when it consumes the CPU and is running in the main memory. It can be either in a ready to run state in main memory or swap memory, sleep state in main memory or swap memory, blocked state in either main memory or swap memory, and finally terminated state. We can see the different states using the diagram shown here. Here we can see that the process is being created using the fork system call, and after being created it enters in the waiting state. In waiting state, process has all the required resources to run. So this is like a queue where different process queues up, and once the turn comes for the process, it switches from the waiting state to the running state. In running state, the process consumes the CPU and executes the instructions. From running state, it can either enter into different states. For example, if the process in running state is blocked by some resource, it can enter to blocked state. Or when the process in a running state executes the sleep instruction, it can enter into the sleep state. Also, once the process CPU time is utilized, it goes back to the waiting state or ready to run state. In this case, all the states are present in the main memory. But since the main memory is precious and the space is of constraint, the swapper swaps the process from the main memory to the swap memory so that the main memory is freed up for some other process. Here we can see that the process at any given point of time can exist in any of the state. So finally, after the process finishes its execution, it is terminated and enters the terminated mode. In next video session, we will learn memory layout of a process. Thank you. Hello and welcome. In this video session, we will discuss the basic memory layout of a process. The different segments of a process are text segment, data segment, stack segment, and heap segment. The data segment also contains initialized data segment and uninitialized data segment, also called as PSS segment. Let's discuss each of the memory segment in brief. The text segment contains the code of the program that is executed. This segment of memory cannot be written so that the code is not altered by any bad pointers. This also means that the text segment is read-only copy. The initialized data segment contains global and static variables that are explicitly initialized with the value in the code. The uninitialized data segment contains global and static variables that are not explicitly initialized in the code. So, the system initializes all the values of the segment to 0. The stack is a dynamically growing and shrinking segment containing local data, also called as the stack frames of the function. One stack frame is allocated for each function that are called. A stack frame stores the function's local variable and function arguments. The heap is an area from which memory can be dynamically allocated at runtime. In next video session, we will learn memory layout of a process in depth. Thank you. Hello and welcome. In this video session, Let's discuss the different segment of memory of a process using a C code as an example. As a note, this program is only for demonstration and does not have any specific use case. So this program starts by creating two global variables. One is initialized and other is uninitialized. The initialized variable is stored in initialized data segment, whereas the uninitialized global variable is stored in uninitialized data segment. The execution of the program begins with main function. All local variables of main function are pushed onto the stack, and the local variables of function forms a stack frame of that particular function. So in this case, all the local variables of main function forms the stack frame. We have variables num1, num2, sum, char pointer, pstr, char pointer buff, and char array stack underscore buff of 20. These are stored onto the stack. But here, if you notice this, char star buff equal to welcome string pointer variable buff is stored on the stack. But the string welcome is not stored on the stack. It is stored in text segment, and buff only points to the memory location of text segment where welcome string is stored. Now let's consider the next variable stack underscore buff of 20. This variable is stored on the stack and it has stack data as its data. The stack underscore buff variable content can be changed or altered by doing string copy and assigning it to a new value. But similar stuff cannot perform on buff because buff is pointing to text segment, and text segment, as we have discussed, is read only, and if we try to manipulate the text segment, we will be getting segmentation fault. Let's see this as an example. We have num1 equal to 10, num2 equal to 20. When we execute the program, this value is being updated on the stack, and when we call add underscore num function, the local variables of this function is pushed to stack frame. If we notice here, we have a int count variable which is static type. Hence, this count variable is not stored on the stack. It is stored under the initialized data segment. Now, this function performs an addition of two numbers and initially stores the result in variable res and returns the value of res to the function which is called. In this case, it returns back to this point where the addNum function is being called, but before returning all the stack frames of this function, addNum will be deleted. That means all the stack variables of add underscore num will be popped back and the stack has shrunken back, and stack now has the stack variables or stack frame of main function alone. Now again, we call add underscore num with a different value of num1 and num2. Num1 equal to 100 and num2 equal to 200. The same process again occurs. It forms a new stack frame for add underscore num function, and when add underscore num returns, all the stack frames of add underscore num function is deleted and the execution returns back to the point from where it is being called. Now, if we go further, we have malloc. Malloc is considered as a dynamic memory allocation, and hence this 20 bytes are stored onto the heap segment. And if we do a string copy of hello to the pointer variable pstr, which points to the heap memory segment where 20 bytes is allocated, It stores data hello as the string. As a note, here pointer variable pstr is stored on the stack, but allocated memory is stored on the heap. Now let's compile this program and let's see the output. We have compiled the program. Now let's run the program. Since we have called addNum twice, we are getting the output two times. Now let's enable this part of the code in which we are trying to alter the text segment. Let's recompile this program. Now let's run this. We can see that we are getting a segmentation fault because we are trying to alter the text segment, which is a read-only. By this, we have covered the different memory segment of a process like code segment or text segment. Text segment is the one where the instruction or the program resides. Then we have initialized data segment and uninitialized data segment, the stack segment in which the local variables are stored, and the heap segment in which the dynamically allocated memory is stored. In next coming video sessions, we will study a very important concept of virtual memory of a process. Thank you.